So in this video, you're going to learn about limited reactants and percent yield. This is an extension of what you should already know about stoichiometry, so it shouldn't be a difficult transition for you. Limited reactants are the reactants in the chemical reaction that limits the amount of product that can be formed. Percent yield is the amount of desired product produced. So your equation for percent yield is the actual yield divided by the theoretical yield multiplied by 100. Well, what is theoretical yield? Theoretical yield is the expected amount of product. It's known as the predicted amount. Limited reactant problems compare with theoretical amounts with the reality. So you compare the theoretical, which is what you were expecting to get, with what you actually got when you conducted the experiment. So you can use the BCA chart to display the calculations for limited reactants. And then the steps for limited reactant problems and percent yield problems are pretty much the same as a stoichiometric problem. So we're going to start with our first example. It says when 0.50 moles of aluminum reacts with 0.72 moles of iodine to form aluminum iodide, how many moles of excess reactant will remain? How many moles of aluminum iodide will form? So the first step is to balance the equation. So we've already done that. You have 2 atoms of aluminum for 3 molecules of iodine. That's going to produce 2 molecules of aluminum iodide. So in order to get this done, we have our BCA chart here, kind of trying to save us a little bit of time. What you need to do is set up your proportions for your BCA chart based upon what the problem gave you. So if you look, it gave you 0.50 moles of aluminum. And then it gave you 0.72 moles of iodine. So you don't have anything for your aluminum iodide yet because it has not been created yet. So you can put a 0 there. So then when we're doing our change, remember we're setting our ratios up according to what our coefficients have told us. So this one is actually a little different, and you're not going to put the coefficient ratios directly in or the mole ratios directly in and multiply. This time you want to do that math separately. So what you're going to have, this is the information that goes in right here, 0.72 moles of iodine. You're going to use the iodine this time as your denominator because what you want to determine is the amount of moles of aluminum. So the problem gave you 0.72 moles of iodine, and then it told you in the chemical reaction that you're going to have 2 moles of aluminum and 3 moles of the iodine. So the moles of iodine cancel. Then you're going to multiply 0.72 moles of iodine by 2 moles of aluminum. And you're going to divide by the 3. So 0.72 times 2 divided by 3 is going to give you 0.48. So that's the number that's going to go here for the change. Remember, it's going to be negative because you need to put it into the chemical reaction in order to get your product. And then the same thing we need to do here for the iodine, but the reverse. So you're going to use the moles of aluminum. So 0.50 moles of aluminum. It's going to be multiplied by the mole ratio of 3 moles of iodine to 2 moles of aluminum. Moles of aluminum will cancel. So then you'll do 0.50 times 3 divided by 2, and you'll get 0.75 moles of iodine. So when you're doing your actual changes, that's what you're also going to plug in here. So remember before we had our simplified answer here. I'm just plugging in with the same answer as there because you can't do all your work and put it in the BCA chart. So you want to make sure you show your work, but do it at a separate point. You're not going to be able to fit that in your BCA chart. So we have, for our change for our moles of aluminum, 0.480. Remember, we started off with 0.50, and then we started off with 0.72 moles of iodine, and according to our calculations, we're going to need 0.75 moles. And then now we can actually use this information to determine which one is our limited reactant. So if you look here, the problem gives us 0.50 moles, and we're going to need 0.48 moles for the reaction to occur. So that's going to leave us with 0.0 2 moles of your aluminum. Then for your iodine, you have 0.72 moles from the problem, and it's saying that you're going to need 0.75 moles of the aluminum for your reaction. So this is your limited reactant because it's saying that you're going to need 0.75 moles for the reaction to actually occur, and you only have 0.72 moles. So whichever one is your limited reactant, you're going to use that amount of moles in order to calculate your products. So here you only have one product, so 0.72 moles of iodine, which was given in the beginning, is going to be multiplied by the ratio of 2 moles of aluminum iodide to the 3 moles of iodine. So your moles of iodine cancel. 0.72 moles times 2 divided by 3 is going to give you 0.480. So that's where this number comes from here. And remember, this is positive because this is what's going to be produced. So you just drop that answer down. And let's go back and read our question. It says, how many moles of aluminum iodide will form? And here's your answer. You'll have 0.48 moles of aluminum iodide form. So for example 2, this is also a limited reactant problem. It says, when sodium hydroxide reacts with sulfuric acid, which is H2SO4, water and sodium sulfate are the products. Calculate the mass of the sodium sulfate produced when 15.5 grams of sodium hydroxide are reacted with 46.7 grams of sulfuric acid. So with our balance equation here, we're going to have 2 molecules of sodium hydroxide plus 1 molecule of sulfuric acid. Then that's going to produce 2 molecules of water and 1 molecule of sodium sulfate. So once again, we're going to do the same thing. We're going to fill in what our before was from the problem. But this time, in order to do that, we're going to have to convert. It gave us grams, but when we're using the BCA chart and we're trying to find the amount of moles, you have to have moles. So this one was a little different in the sense that you had to actually do the math. So we're going to bring this board back up and show you your math using this board. So the 15.5 grams of sodium hydroxide, you're going to get rid of that grams per sodium hydroxide by finding the molar mass. So in sodium hydroxide, you have sodium, which is 23, plus oxygen, which is 16, plus the 1 for the hydrogen. That gives you 40 grams, so that's going to be your denominator. You're trying to get moles, so that's going to go in your numerator. So 15.5 times 1 divided by 40 gives you 0.388 moles of sodium hydroxide. So now we need to do the same thing for sulfuric acid. So it gave you 46.7 grams. You need to find the molar mass. So you have 2 hydrogen, 1 times 2. Sulfur's mass is 32 plus 16 for the mass of oxygen, but you have 4 oxygen, so you multiply by 4. That gives you 98 grams. So the grams per sulfuric acid cancels. So 46.7 times 1 mole, because that's what you want your answer in, divided by 98. So that gives you 0.477 moles of the sulfuric acid. So those are the numbers we're going to use as we go back to our problem. So if you see here, 0.477 moles of sulfuric acid. Now we need to set up those ratios for the BCA chart based upon those numbers. So you had 0.388 moles of your sodium hydroxide, and then you had 4.77 moles of your sulfuric acid. Remember, these products have not been made yet, so you don't have anything there. So same thing here. We want to go ahead and do the math so we don't have to fill that in into our BCA chart. So I did my math up here so you can see where it will fall down here. So we're going to start with trying to figure out our amount of sodium hydroxide, then our sulfuric acid, and then we'll do the water and the sodium sulfate. So you want to use the amount of sulfuric acid calculated before when we converted from grams to moles in order to find the sodium hydroxide. So 0.477 moles of sulfuric acid is going to be set up from the ratio of the coefficients of sodium hydroxide, which is 2 molecules or 2 moles, and then 1 mole of the sulfuric acid. So moles of sulfuric acid cancel. 0.477 multiplied by 2 divided by 1 gives you 0.954 moles of sodium hydroxide. So that's where that goes. Remember, you're putting it into the reaction to produce product, so it's going to be negative. And then we're going to do the same thing to get your amount of sodium hydroxide, your amount of sulfuric acid using sodium hydroxide. So 0.388 moles of sodium hydroxide. Your amount of your mole ratios from your coefficients come in. So 1 mole of sulfuric acid, 2 moles of sodium hydroxide. So moles of sodium hydroxide are going to cancel. So then you have 0.388 moles, 0.338 times 1 mole of sulfuric acid divided by 2. That gives you 0.194 moles of sulfuric acid. So that's going to come into your change part of your chart. It's going to be negative because you're putting it into the reaction. So now we're going to actually do our products, but before we do that, we need to determine which one was our limited reactant. So here the problem gave you 0.388 moles. It's going to take 0.94 moles for the reaction to actually take place. So this is going to be your limited reactant. And then you have 0.477 moles given, and it takes 0.94 moles. So you just subtract the difference. So 7 and 4 is 3, 7 and 9. You have to make this 17. So then 17 minus 9 gives you 8. You reduce the 4 to 3. 3 minus 1 is 2. So you have 0.283 moles of your sulfuric acid. Now we need to do our products by using our limited reactant amount. So if you go back to what your before was, we're going to do 0.388 moles of sodium hydroxide because that was our limited reactant. You're going to set up your ratio of moles of water to moles of sodium hydroxide, so 2 to 2. So 0.388 times 2 divided by 2 gives you 0.388. Remember, 2 to 2 reduces to 1, so you're just multiplying 0.338 by 1. So you get 0.338 moles of water. That is positive because you're making that. So then once we get to our sodium sulfate, because that's what our final product is, we're going to use that same 0.338 moles of sodium hydroxide because that was your limited reactant. So 0.388 moles of sodium hydroxide is going to be set up to the ratio of sodium sulfate and sodium hydroxide. So 0.388 moles of sodium hydroxide multiplied by 1 mole of sodium sulfate divided by 2. So, 3.88 times 1 divided by 2 gives you 0.194. Remember, that's positive because you just produced that. That was made in the chemical reaction. So you're going to drop these numbers down for your after. So after reaction has taken place, you don't have enough of your sodium hydroxide. You are left with 0.283 moles of sulfuric acid, and then you have 0.388 moles of water and 0.194 moles of sodium sulfate. But if you go back, the question says calculate the mass of the sodium sulfate produced. So you need to take your number for your sodium sulfate, which is 0.94 moles, and convert it to grams. So we're going to go back to our board that shows us setting up our math. So mole to mass here, 0.94 moles of the sodium sulfate. And then what you have here is your molar mass, because that's what you want your answer in. You're going to just put 1 mole at the bottom because you want to get rid of that unit. So 0.94 times 142 grams of sodium sulfate divided by 1 gives you 27.5 grams of sodium sulfate. And here you have the math for how did you get the 142 grams for your molar mass. So now we're getting into some percent yield. So this is a percent yield example. Specifically in this problem, you're looking for the theoretical yield. So it says you eat 180 grams of glucose, which equivalizes to 90 M&Ms. It says if glucose is C6H12O6, it reacts with oxygen gas to produce carbon dioxide and water. How many grams of oxygen will you have to breathe in to burn the glucose? So doing the same thing, we have to start with our balanced chemical equation. So you have 1 molecule of C6H12O6 plus 6 molecules of oxygen gas plus you produce 6 molecules of carbon dioxide, and then you also produce 6 molecules of water. So this equation should actually be familiar to you because this is cellular respiration minus your ATP. So because it gave us the grams of glucose, in order to fill in our BCA chart, we're going to have a conversion take place. So 180 grams of your glucose, and if you did the molar mass for glucose, 12 times 6 for your carbon, 1 times 12 for your hydrogen, and 16 times 6 for your amount of oxygen is going to give you 180 grams. So your molar mass is also 180 grams, and what you want your answer is in moles. So 180 times 1 divided by 180 gives you 1 mole of C6H12O6. So that's what's going to go in our BCA chart for our glucose, 1 mole. So here we have an excess amount of oxygen because it doesn't tell us how much oxygen yet in the background is needed to do the actual process of breaking down the M&Ms or the glucose specifically. So excess, and then remember our carbon dioxide and water has not been produced yet, so you have zeros for there. This part is going to be more familiar, more like what you did for stoichiometry, because we're going to go back to doing those mole ratios and multiplying. So starting with what they gave us, which was the glucose. So we have 1 molecule of glucose. So, and our coefficient is also 1 molecule, so a 1-to-1 ratio. The amount of glucose moles that we know about are 1, so times 1 mole. That's going to give us a negative 1 mole amount. Remember, this is what's going to be used to produce the carbon dioxide in the water. So then we're going to go to our excess amount. In the problem, we have 6 moles to 1, so it's a 6-to-1 ratio. You also multiply by 1 because that's the amount of moles that we are given. That gives you a negative 6 mole amount for oxygen. Remember, this is what's going to be used to produce your carbon dioxide in your water, so it will be negative. And then we're going to go to our products. So you have a 6-to-1 ratio for carbon dioxide to glucose. You multiply that by 1. Remember, this time it's going to be positive because this is what you're getting out of the reaction, so positive 6 moles. Same thing with your water, 6-to-1 ratio. It's also positive because you're producing this. That's going to give you 6 moles. So then we're going to bring down what we have. Because this was our excess reagent, we can just go ahead and write excess. We had no moles left of our glucose, but we did make 6 moles of carbon dioxide and 6 moles of water. So let's go back to find out what our question asked us, which was how many grams of oxygen will you have to breathe in to burn the glucose? So this is our amount of moles of oxygen, but we need to know how many grams of oxygen. So you use 6 moles of oxygen to make this reaction happen, but we need to find out the amount of moles. We need to find out the amount of grams. So we're going to do a mole to grams conversion. So 6 moles of oxygen gas. We're going to get rid of moles, so that's going to be our denominator. Then you're going to multiply by 32 grams of oxygen. 6 times 32 divided by 1 is 192 grams. And our last problem is also a percent yield problem. This time you're actually going to end up calculating the percent yield. So the problem says, suppose 4.61 grams of zinc was allowed to react with hydrochloric acid to produce zinc chloride and hydrogen gas. How much zinc chloride should you get? Suppose what you actually recovered was 8.56 grams of zinc chloride. What is your percent yield? So again, they gave us our gram amount of zinc, so we need to do a conversion to get the mole amount to use the BCA chart. So right here we have our conversion, 4.61 grams of zinc, and then you want to get rid of grams of zinc, so you use the mass of zinc, which is 66 when you round, and then you're going to have 1 mole of zinc. So 4.61 times 1 divided by 66 gives you 0.0698 moles of zinc. So that's what we're going to plug in here for our BCA chart. Keeping in mind our equation was already balanced, so those are the numbers that we're going to use for our change. We did not find out how much hydrochloric acid, so that's going to be in excess. And then we don't know what these two amounts of product are yet because the reaction is not taking place yet. So then we're going to do our change. So then if you look here, 1-to-1 ratio of zinc. We're going to multiply by the amount of moles that we know about. So that's 0.0698. That's going to give us a negative 0.0698 moles of zinc. We're going to do the same thing with our excess amount, which is a 2-to-1 ratio. And it's going to be negative because you're using that to determine the amount of moles for everything else. So 2 times 0.0698 moles gives us a negative 0.1396 moles. And then here we're going to get to our product, so they're actually going to be positive amounts. So 1-to-1 ratio is going to give you a positive 0.0698 moles. And then you have another 1-to-1 ratio. So you can get another positive 0.0698 moles. So now it's time to do our math to figure out what are we left with. So here we're going to be left with nothing. So for our active here, it's going to be excess, so it doesn't matter. And then here we're just going to bring down the amounts of our products. Both of them happen to be 0.0698 moles. So if you go back to what the problem asked you, suppose you actually recovered 8.56 grams of zinc chloride. What's your percent yield? So in order to do this, we need to go back and determine the grams now of zinc chloride. So we have to do the mole to grams conversion. So 0.0698 moles of zinc chloride, which is what we got on this side over here. So that's going to be divided by the amount of moles, which to just get rid of moles is 1. So 0.0698 moles of zinc chloride. Moles of zinc chloride are going to cancel. That's going to be multiplied by 136 divided by 1. You get 9.49 grams of zinc chloride. Percent yield equation is actual divided by theoretical multiplied by 100. So remember it said, suppose you actually recovered 8.56 grams. But according to this, our theoretical is 9.49 grams. So 8.56 divided by 9.49 multiplied by 100. You get 90%. So your percent yield for this problem is 90%. So use worksheets 2 and 3 to help you go through and practice this process. Good luck.